Bismillahirrahmanirrahim. Assalamu alaikum, dear students. Welcome to the online lecture on control systems theory. Today we are going to discuss block diagram algebra. So before we study block diagram algebra, we need to ask ourselves this question, that why do we need to learn block diagram algebra? So the answer is very simple, that when you work in the classroom while studying control systems theory, you are mostly dealing with a block diagram that involves one controller, one plant, and there is a single feedback loop, and you do all the analysis based on that. And if you go to the industry, or if you are working professionally with a complex system such as a smart luxury vehicle or an aeroplane or something complex such as satellite, then you might have many systems connected together, some in series, some in parallel, and there might be multiple controllers and multiple feedback loops in the system. So in such cases, we need to be able to simplify those systems and study the overall properties of the system and overall transfer function of the system. And for that reason, we are studying the block diagrams. So in summary, we want to study block diagram algebra because we want to be able to simplify complex block diagrams and to be able to calculate transfer functions of those complex systems. So I begin with a very classical block diagram in control systems theory that you mostly see in your classrooms. This involves one controller, a plant, G of S, controller is C of S, and the sensor in the feedback loop, which is H of S. So the block diagram is showing you that there is input R of S and output Y of S, and there are two disturbance signals, D1 of S and D2 of S. If we want to calculate the equation for the output in this simple block diagram, we still have to go through a fairly complex set of mathematics. But before we do that, I just want to introduce you to the language of block diagrams. So in terms of language, this circle with plus and minus signs, this is called summing point. So this is a summing point in a block diagram. And then a block with a transfer function inside, it's called functional block. Then there are signals in the block diagram such as R of S, E of S, Y of S that you can see in the current block diagram. Then finally there is a branching point. So branching point, what it does is it basically creates a copy of the signal and sends it to the branch. So in a branching point, same signal is conveyed to both ends, or even if there are more than two ends, same signal goes everywhere. Okay, so next we look at the equations governing this block diagram. First of all, you can see in the block diagram that Y of S is basically a sum of D2 of S and V of S. This you can see in the block diagram. And if you look at V of S is basically G of S times U of S plus D1 of S. And then if you look at the U of S, it is basically E of S times C of S. And finally, if you look at E of S, then E of S is R of S minus H of S times Y of S plus N of S. So these are the equations that govern this block diagram, and we can use these equations, like for example in the equation for Y of S, if we substitute the expression for V of S, and in that expression we substitute the expression for U of S, and in the expression for U of S we substitute the expression of E of S, then what we get is the equation at the bottom of the slide. So this is a fairly complicated equation, but this equation is basically the expression for Y of S in the given block diagram. And still you can see that there is Y on the left hand side and there is a Y on the right hand side as well. So we need to, if we really want to calculate an expression for y of s, we need to combine all the terms involving y of s on the right hand side and on the left hand side. So we go to the next slide and we copy the last equation from the previous slide, and what we do is we multiply everything out, and once we multiply everything out, you can see that on the right hand side there is a single term involving y of s. We bring that term to the left hand side, and here it comes, and this left hand side becomes y of s plus g of s, c of s, h of s times y of s. And then what we do is we take y of s common in the left hand side excuse me, and then in the next slide we copy the last equation from the previous slide, and still we have y of s common on the left hand side. And what we do is we divide by the expression on the left hand side, the multiplier of y of s on the left hand side, by each term on the right hand side, and then we get final expression for y of s. Now if you look at this final expression for y of s, you have to notice certain things. So first of all, look at the relationship, look at the term involving r of s on the right hand side. The term involving r of s, the numerator of that term is g of s, c of s. And if you look at the block diagram and you see the direct path from r of s towards y of s in the block diagram, you see that in that direct path between r of s and y of s, there are two blocks, c of s and g of s. So numerator of the term that is being multiplied with r of s, that numerator is basically the direct path between y of s and r of s. Similarly, if you look at the term involving d1, the numerator is just g of s. And if you look at the block diagram, the direct path from d1 to y involves just one block, that is g of s. And similarly, if you look at the term involving d2 of s, the numerator is 1. And if you look at the block diagram, the direct path between d2 of s and y of s has no functional block in the way. Similarly, the n of s has direct path g of s, c of s and h of s, because you have to follow the arrows of the block diagram. If you start from n of s, you have to go through h of s and through c of s and g of s, and finally you reach y of s. So far our discussion leads to this idea that relationship between input and output involves direct path divided by 1 minus loop gain. So 1 minus loop gain, if you look at the denominator, so loop is common in the block diagram, and so loop gain is the same for every signal. Direct path is different, but the loop gain is same for every signal, and the denominator of each term on the right hand side is same basically, and that is 1 minus loop gain. So loop gain in this case is negative. That is why we have 1 plus g of s, c of s, h of s, in which minus c of s, g of s, h of s is the loop gain, and 1 minus loop gain is the expression for the relationship between y of s and different inputs in the block diagrams. So let me illustrate this idea of direct path over 1 minus loop gain through a simple example. Look at this simple block diagram where we have just one input r of s and one output y of s. So if we look at this direct path between r of s and y of s, so direct path involves two blocks, c of s and g of s. So direct path is c of s multiplied by g of s. And then when you look at the loop gain, so I have highlighted the loop in red. So the loop involves three blocks, c of s, g of s and h of s. And furthermore, the loop also involves a negative sign. So loop gain in this block diagram would be minus c of s, g of s and h of s. And if we apply our formula direct path over 1 minus loop gain, since the loop gain is minus C of S G of S H of S, 1 minus the loop gain will be 1 plus C of S G of S H of S. So the transfer function will become Y of S over R of S is equal to C of S G of S divided by 1 plus C of S G of S into H of S. So this is how we can calculate the transfer functions of a single loop block diagram. We can just select any output and any input, and if there is only one loop in the block diagram, we can calculate the transfer function directly by using the formula direct path over 1 minus loop gain. But let's just move forward and look at slightly complex problem. For example, this problem. So here there is a block diagram with 3 loops, loop containing H1, loop containing H2, loop containing H3, and this is a fairly complex block diagram, and we want to calculate the transfer function between R of S and Y of S. We cannot use the formula direct path over 1 minus loop gain here because there is not just single loop. So we can apply that formula only on the single loop block diagram. So what do we do here is that we first need to simplify this block diagram by some manipulations, and then after simplification maybe we can calculate the transfer function between Y of S and R of S. So for simplicity I have omitted the argument S from all the transfer functions in the blocks and all the signals, but it is understood that all the signals and transfer functions are in Laplace domain. So our objective is to find transfer function Y over R in this fairly complex block diagram. So I've copied this block diagram into the next slide, and I've highlighted a link entering the block H2. So the problem with this link is that this link is basically branching out from the middle of a loop. So there is a loop excuse me, there is a loop G3 G4 H1, and in the middle of that loop this branch is going out. We want this branch to be like we want this branch to be from not coming out from the middle of the loop but from the side of the loop. We want to make our loop independent of this branch. Why do we want to do this? This will be clear shortly, but for now just may note this, that we cannot change the system. Remember that this block diagram may be representing some original physical system installed in an industry, so we cannot change that physical system. What we can do at best is we can find the equivalent model of the physical system, and the equivalent model that we find might be easier to solve than the original model. So here in the original model we have a branch where some signal, let's say signal A is going into the block H2. If we change the rear end of the branch, then what happens is that the signal, instead of signal A going into the block H2, signal A times G4 will be going into the block H2, and the signal going into the summation point will become A times G4 times H2, whereas in the original block diagram the signal going into the summation point after H2 was A times H2. So there is an extra G4 due to changing the position of the rear end of the branch. We need to take care of this extra G4. So what we do is I copy this block diagram in the next slide, and we convert this block diagram into this equivalent block diagram. In the equivalent block diagram you can see that I have shifted the rear end of the branch. I have basically shifted the branch out of the loop G3 G4 H1, And to keep the block diagram same, to preserve the transfer function between y and r, I have changed the block h2, and now the new block is h2 divided by g4. Now what this h2 divided by g4 does is that when the signal a times g4 comes, then g4 is cancelled out and a times h2 goes forward as was going forward in the original block diagram. So we have manipulated the block diagram without disturbing the transfer function between the input r and the output y. So this manipulation allows us to do some further simplifications. For example, in the next slide I have redrawn the manipulated block diagram, and if you look at this loop now, there is no branching from the middle of this loop. So this loop is now independent, G3, G4, H1. So we can basically call this loop x1 and find the transfer function of x1 using our previously developed formula, which was direct path divided by 1 minus loop gain. So if we do that, the block diagram simplifies into something that is shown on at the bottom of the screen. So this block diagram is now fairly simple because the whole loop G3, G4, H1 is now represented by a single block x1, and x1 is excuse me, the transfer function for the x1 is G3, G4 divided by 1 minus G3, G4, H1, which is direct path divided by 1 minus loop gain. So this is how we have significantly simplified our block diagram, but this simplification is still not enough because we still have two loops in the block diagram and we cannot directly calculate the transfer function between y and r. So we will perform further simplifications on this block diagram. So in the next slide I copy the bottom simplified block diagram, and I also copy the expression for x1. And next what we do is we look at this loop. So the loop g2 x1 and h2 divided by g4. This loop can also be simplified into a single transfer function that we can call x2. So x2 can be found by using the same formula, direct path divided by 1 minus loop gain. So once we replace this loop with a single transfer function x2, the resulting diagram is shown at the bottom of the slide, and the expression for x2 will be g2 x1 divided by 1 minus g2 x1 h2 divided by g4. So this here in the expression for x2, you can basically take g4 in the denominator as LCM, and you can simplify the expression for x2 a little bit. So now look at this simplified block diagram at the bottom of the slide, and this is now just a single loop block diagram, the kind of block diagram that we know how to deal with. So we can find the transfer function between y and r, and that would be direct path divided by 1 minus loop gain. Notice that the loop in this case is a negative loop, so the transfer function between y and r will be g1 x2 divided by 1 plus g1 x2 h3. So finally, after certain simplifications, we have successfully calculated the transfer function between y and r. But we are not done yet because this transfer function is in terms of x2, and x2 is in itself is a function of x1, and x1 is also has its own expression that you can see on the left hand side of the slide. So next what we do is we come back. So one thing you have to notice is that although we have manipulated the block diagram, we have preserved the properties of the block diagram in such a way that the transfer function between y and r that we have calculated on this slide is basically applicable to this original block diagram. This is the original block diagram that we have initially, that we manipulated. And this block diagram has the same transfer function that we found in the previous slide, which is y over r is equal to g1 x2 divided by 1 plus g1 x2 h3. So next what we do is we substitute the value of x2 in the transfer function. Notice that x2 appears at two places in the transfer function of y over r. It appears in the numerator and it appears once in the denominator. So if we substitute on both places, then we get this kind of expression. Although this is a fairly messy expression, but you can notice that the term in the numerator and the term in the denominator has a common entity, which is g4 minus g2 x1 h2. If we take g4 minus g2 x1 h2 as LCM in the denominator, then the LCM would be cancelled out with the term on the numerator. So the expression will become like this: g1 g2 g4 x1 divided by g4 minus g2 x1 h2 plus g1 g2 g4 x1 h3. So this is simplified by taking LCM in the denominator in the previous expression for y over r. Now I copy this expression for y over r in the next slide, and we get like this is so far the transfer function for the original block diagram that we had. And in this transfer function we still have x1 at certain places. So the expression for x1 is given on the left hand side, which I have been copying through the slides. So if you use this expression and substitute it, then this is the form of your excuse me, of your transfer function. And here once again you can take the LCM in the denominator and cancel things out. And once you do the I have just copied this equation from the previous slide, and once you do these cancellations after taking LCM in the denominator, then you get this expression. So this expression, you can still further simplify this expression, because if you look closely, there is g4 in the numerator. Actually there are two g4s in the numerator, and there is g4 in every term of the denominator as well. So you can take g4 common from the numerator and denominator and cancel it out. Once you do that, then you get this kind of expression. This is copied from the last slide. After cancelling out g4, you get the expression in the red box. So the expression in the red box is basically fully simplified transfer function between y over r in the original block diagram. Now I want you to look very closely at this transfer function, the final transfer function, and let's try to study how it correlates with the original block diagram. So if you look at the original block diagram, the direct path between r and y is g1, g2, g3, g4. So the direct path between r and y has g1, g2, g3 and g4 blocks involved. And if you look at the loops, there is a loop g3, g4, h1, and there is g3, g4, h1 term in the denominator of the final expression. Then there is a loop g2, g3, h2. There is a loop g2, g3, h2, and similarly there is a g2, g3, h2 expression in the denominator. And then there is another loop g1, g2, g3, g4 and h3. So this is the third loop, the biggest loop, and its expression is given in the denominator g1, g2, g3, g4, h3 with an opposite sign compared to the other two loops. That's because this loop is a negative loop. This loop has a negative sign in the feedback summation point. So if we try to make something out of this exercise, then what we do is like it looks like that the transfer function of the whole block diagram is something like direct path divided by 1 minus sum of all loop gains. So this is quite interesting, because if this is true, then we can calculate the transfer functions for block diagrams having multiple loops without having to do any manipulations and without having to do any block diagram algebra. We can just look at the block diagram and find the direct path transfer function and find the gains of all the loops, and we write the transfer function as direct path over 1 minus sum of all loop gains. So for example, if I give you a new block diagram, then if I am to apply this formula of direct path divided by 1 minus sum of all loop gains, then the transfer function for this block diagram would be g1, g2, g3, g4, which is direct path, divided by 1 minus g3, g4, which is one of the loops, g2, g3, which is another loop, and minus g1, g2, which is the third loop in the system. So let's see if this actually is true, and if it is, then it's great. But since we have found this formula by using just one example and no solid mathematical derivation, so we just have to check this formula whether it applies to different examples or no. Right, so in order to check this formula, we will calculate the transfer function between r and y for this block diagram using the traditional block diagram simplifications as we did before. So here I have highlighted a branch link that is basically emerging from the middle of one loop and landing in the middle of another loop. So in order for me to be able to simplify this block diagram, this branch has to be adjusted as we adjusted the branch in the previous example. So first adjustment that we need to make in this branch is that the head of this branch should fall outside the loop g1, g2, and in order to make this head fall outside the loop, we will need to do some changes in the link, and the second change we need to do is that we need to put the tail of the link outside the loop g3, g4. So how do we do that? For adjusting the tail, it is similar to what we did before. We need to divide by g4 in the link, but in order to adjust the head of the link, since g1 was initially not included, so the signal was entering signal from the red link was entering into a summation point which was after g1, and now we wanted to enter at a summation point which is before g1. So g1 is being added into the path which was not there before in the original diagram. So if we adjust the head and tail of this red link, then we have to divide by g4 because of the adjustment of the tail. The adjustment of the tail has included g4 block into the path of the link, and the adjustment of the head has included g1 block into the path, overall path. So that's why we add a block to the link on the top of the diagram. That block is 1 over g1 and g4. So this block 1 over g1 and g4 compensates for the changes we have done to the head and tail of the branching link in the block diagram. So the top diagram and the bottom diagram are equivalent to each other, but the bottom diagram is easier to deal with and easier to simplify, as we will do in the next slide. So I copy the bottom diagram into the next slide, and we see that we can basically, there is a loop g1 g2. We can convert it into a single transfer function and call that transfer function x1 as we did before. And then there is a loop g3 g4, and we can convert this loop into a single transfer function as well, and we can call that transfer function x2. If we do this simplification, we get a resulting block diagram which has a single loop where the direct path is x1 and x2, and the feedback path is 1 over g1 g4. So x1, as you can see in the top block diagram, x1 loop is g1 g2 divided by 1 plus g1 g2 because it's a negative feedback loop. So the denominator has a plus sign. Similarly, x2 is g3 g4 divided by 1 minus g3 g4 because it is a positive feedback loop. So that's why denominator has a negative sign. Okay, so we have derived x1 x2 and we have simplified the block diagram to a single loop. So now we can basically calculate the transfer function between r and y, which will be direct path divided by 1 minus loop gain. And if we do that, we get y over r equals x1 x2 divided by 1 minus x1 x2 over g1 g4. So we can, so this is the transfer function for the original block diagram that we simplified. So using the simplified block diagram, we get the transfer function for the original block diagram, because in the process of simplification we have preserved the original transfer function. So this is the original block diagram again, and it gives the transfer function as we derived in the previous slide. So if we simplify, take LCM in the denominator, then we get y over r equal g1 g4 x1 x2 divided by g1 g4 minus x1 x2. So now what we want to do is that in this y over r transfer function, we want to substitute the value of x1 and x2. So if we do just that, then we get this kind of transfer function, and we can take the LCM in the denominator as we did in the previous example. And if we take the LCM in the denominator, the LCM will cancel out with the term in the numerator, as was the case in the previous examples. So this equation will simplify to excuse me. This equation will simplify to y over r equals g1 g2 g3 g4 divided by 1 plus g1 g2 1 minus g3 g4 minus g2 g3. So here not only I have taken the LCM in the denominator, but I have also cancelled out the term g1 g4 from the numerator and the denominator. So I have done two simplifications in one step on this slide. And the bottom equation is the I can further simplify the bottom equation, the equation at the bottom of the slide. So if I've copied it on the next slide, and if I multiply out the terms in the denominator, then I get this equation. Now if you look at this equation looks like looks very similar to something like direct path over 1 minus sum of all loop gains, but let us check whether it's exactly that or not. So I've repeated the equation here in a more precise, like presentable way. I have put some terms inside the bracket for ease of understanding and presentation. So this the expression in the red box, that is the expression that we were expecting from the block diagram. So in the start, when we before we started doing calculations on this block diagram, we predicted that the transfer function would be what is written in the red block, that is y over r equal g1 g2 g3 g4 divided by 1 minus sum of all loop gains. If you look on the top expression, which we have just calculated, then there is a difference of there is an extra term in the denominator, which I have captured in a thin red block, rectangle. So what is this extra term? Where does this term come from? So this extra term is basically, if you look at the diagram, block diagram, there is something special about this block diagram. That special thing is that the loops G1, G2 and G3, G4, the loop G1, G2 is completely separated from the loop G3, G4. So these loops do not overlap with each other. On the other hand, the loop G2, G3 overlaps with both of the other loops. So there is this thing different. And if you look at this additional term that we have got in our calculation, this is minus G1, G2, G3, G4. Minus G1, G2 is the loop gain of one of the loops that is separate from the other loop, that is G3, G4. So it seems that the transfer function in this case is direct path divided by 1 minus sum of loop gains plus product of non-touching loops. Okay, now we have this is the third formula that we have discovered in this lecture, and still we wonder whether this formula is applicable to all possible block diagrams. But before I comment on that, I just want to clarify that in the previous example there was no non-touching loop, and in this example there are two non-touching loops that are G1, G2 is non-touching with G3, G4. So the formula that we have derived here, if we apply the same formula to the previous example and even to a single loop transfer function block diagram, it will be applied to both types of block diagrams. So this formula that we have derived, direct path over 1 minus sum of all loop gains plus product of non-touching loops, this formula applies to the diagrams that block diagrams that do not have any non-touching loops. If the block diagram does not have any non-touching loop, then simply the product of non-touching loop will become 0, and the formula will be reduced to direct path over 1 minus sum of all loop gains. And if there is only one loop in the system, then not only the product of non-touching loops will be 0, but also in the sum of all loop gains there will be just one loop, that is the only loop in the block diagram. So the formula will be reduced to direct path over 1 minus loop gain. So this formula, although it is applicable to all the examples that we have done so far, but still we wonder what is the ultimate solution. So next we go towards the ultimate solution, which is basically Masson's rule. Before I describe the Masson's rule to you, I have to describe something that is used for applying the Masson's rule, which is signal flow graph. A signal flow graph is something that is similar to a block diagram, but there are some key differences. To illustrate that, I have presented this block diagram, which is a simple one, and if I want to convert this block diagram into a signal flow graph, then the signals in this block diagram will become the nodes in the signal flow graph, and the blocks in this diagram will become links in the signal flow graph. So the resulting signal flow graph will be something like this. Excuse me. So you can see in the signal flow graph there are 4 nodes. Each of these 4 nodes represent a signal in the corresponding block diagram, and there are 4 links, 3 forward links and 1 feedback link. So the forward links represent the blocks in the block diagram. Link that is between R and E is 1. 1 means that there is no block between R and E signals, and the link C and the link G represent blocks C and block G in the block diagram. The link minus h in the signal flow graph on the right side, the link minus h represents the block h in the block diagram. So the idea of Mason's rule is to convert block diagram into directed graph and use linear algebra to find the transfer function. But I also have to specify certain language that is used in the signal flow graphs. An input node in the signal flow graph is such a node from which all links are going out. Any node, excuse me, any node from which all the links are going out and no link is coming in, that is input node. In the diagram that is shown on the slide, top right part, R is the input node. An output node in the signal flow graph is a node for which all the links are going in. So in our signal flow graph, Y is the basically Y is not the output node because not quite all the links are going out. If I draw it a little bit different, then Y could have been the output node. If I had drawn one more node and defined one more signal, then there would be an output node. So far the way I have drawn this signal flow graph, there is no output node. Maybe yes. So sorry, input node is where all the links are going out, and the output node is where all the links are going in. So there is no output node in the signal flow graph that I have drawn, but there is input node which is R. Direct path in a signal flow graph is connection from input node to the output node, and similarly a loop in the signal flow graph is any path that starts and end at the same node. If you take any path inside the flow graph that starts and ends at the same node, that will be considered as loop. So for example, if you take the node E, from node E the path is from E to U and U to Y and from Y back to E. So there is a loop in this signal flow graph from E to U and U to Y and back to E. Okay, so these are the nomenclatures relevant to the signal flow graph: input node, output node, direct path, directed path, and the loops. A loop is touching. This is the language in signal flow graphs. A loop is considered to be touching a direct path if the loop and the direct path have at least one node in common. So in this case, there is only one loop and there is only one direct path. So both are touching because node E, node U, and node Y, three nodes are common in the loop and the direct path. Two or more loops in a signal flow graph are considered to be touching if they have at least one node in common. So in signal flow graph, it is easy to determine whether any two loops or three loops are touching or non-touching based on whether there are common nodes in those loops or not. Similarly, it is easy to determine whether a direct path is touching a loop or not touching a loop based on the nodes that are part of the direct path and the loop. If there is any common node, then those are considered to be touching. Otherwise, if there is no common node, then a direct path and a loop or two loops are considered to be non-touching. Next, I describe the Mason's rule. Mason's rule is basically the formula for determining the transfer function from any block diagram, no matter how many loops and direct paths the block diagram have, you can find the transfer function without having to perform any block diagram algebra or anything, just by applying Mason's rule. Mason's rule is sum of all direct paths multiply by delta divided by a common delta. So direct path I multiply by delta I divided by delta. So sum over all such direct paths. So this is Mason's rule. If a system has, if a block diagram has 3 direct paths, then there will be direct path 1 times delta 1 plus direct path 2 times delta 2 plus direct path 3 times delta 3 divided by delta. Now we need to define what is the definition of delta 1, delta 2, delta 3 direct path. We already know what direct path is. We need to define what delta 1, 2, 3 and the denominator delta. So direct path, the ith direct path is the transfer function of ith dp sub I is the transfer function of ith direct path from R to Y. So from input node to output node, there might be more than one direct paths. So ith dp sub I is the transfer function of ith direct path from input node to the output node. Then delta is 1 minus sum of all loop gains plus sum of gain products of all pairs of non-touching loops. So this we have seen in the previous in the last example that we did, that there were two non-touching loops, and there was, like, in the denominator there was 1 minus sum of all loop gains plus gain product of the pairs of non-touching loops. So there was only one pair in our example. So we had that. If there were more than non-touching pairs of loops, then we would have more terms in the corresponding delta. And delta does not finish at the pairs of non-touching loops. It goes on minus sum of gain products of all triples of non-touching loops plus sum of gain products of all quadruples of non-touching loops minus sum of gain products up to so on 5 loops at a time, 6 loops at a time, however many non-touching loops are there. So all have to be catered in the delta. So delta could be quite complex. So I repeat what delta is. Delta is basically 1 minus sum of all loop gains plus sum of gain products of all pairs of non-touching loops minus sum of gain products of all triples of non-touching loops and plus sum of, so there is minus plus minus plus, the sign is toggling between minus and plus, and after that there are like gain products. So first there are gain products of pairs, then there are gain products of triples, and then there are gain products of quadruples, and so on. Delta I is basically same, the definition of delta I is same as delta, but all the loops that are touching the ith direct path should be dropped. So we do not count any loop that is touching ith direct path while calculating delta I. So this is the definition of delta I. So overall Mason's rule is sum over all direct path I multiplied by delta I divided by delta. So this is Mason's rule. Now we just look at an example. So for example, let us suppose we are given this signal flow graph. In this signal flow graph you can clearly see that R is the input node and Y is the output node, because all links are going out of the R. There is no link coming into the node R. So it is the input node, and all links are coming into the Y. There is no link that is going out of the node Y. So that is why Y is the output node. And there are quite a few loops in this signal flow graph, and we will see how many loops are there. First of all, let's see that what are the direct paths between R and Y. So you can see I have highlighted one direct path, and this direct path between R and Y is G1, G2, G3, G4 and G5. So this is the transfer function of direct path 1 between R and Y. So R and Y has this direct path, but this is not the only direct path between R and Y. If you look closely, there is another direct path which is highlighted right now, which is excuse me, G1, G6, G4, G5. So you can take an alternate path from R to Y, and the transfer function of this direct path will be G1, G6, G4, G5, as I have written on the bottom of the slide. And similarly, if you look again, you can find a third direct path between R and Y, and that is G1, G2, G7. So the transfer function of the third direct path is G1, G2, G7. So there are three total direct paths in in this signal flow graph. And next we look at the loops. So first loop that is quite obvious one in this direct path in this signal flow graph. I have highlighted this in the loop in this slide. Look at the red highlighted links. The loop is minus G4H1. So the first loop in this signal flow graph is minus G4H1. By the way, the numbering of the direct path or numbering of the loops does not matter. If you call direct path 1, which I have called, if you call it direct path 2 and you renumber it, numbering does not matter as long as you identify all of the direct paths and all of the loops. It does not matter which loop you call L1 and which loop you call L2. So we are calling minus G4H1 this loop as L1. Next we see that there is another loop in the system in the signal flow graph, which is highlighted in this slide, G2, G3, G4, G5 and H2. So this is also negative loop, minus G2, G3, G4, H5, G4, G5, H2. So this is the we call this L2. This is the second loop in the signal flow graph. Third, we can also see that there is another way of creating a loop which is slightly different from L2, and that is G6, G4, G5, H2. And this is also negative loop, minus G4, G5, G6, H2. So this is the third loop. And finally, the fourth loop is G2, G7, H2, minus G2, G7, H2. So these are the four loops. I have gone through them quite quickly. You can rewind the video and pause the video and absorb all these loops and their transfer functions, and you can see for yourself that these are indeed the loops in this signal flow graph and the direct paths. Okay, so but there is something to notice here, that is that L1 and L4 are non-touching loops. You can see that in L4 the nodes that are involved in L4 are the third, fourth and seventh node. So node number, if I had numbered these nodes, the third node from the right, the fourth node from the right and the seventh node from the right, these nodes are part of L4, whereas node 5 and 6 are part of L1. So 5 and 6 are not part of L4, so L4 and L1 have no node in common, so they are non-touching. So what we do is that we have just one pair of non-touching loops and all other loops are touching. So we have the Massons rule, and we apply the Massons rule on this example, and we see that the delta will be 1 minus sum of all loop gains plus gain products of non-touching pairs of loops. So we only have one pair of non-touching loops, so there is in the summation of gain products of pairs of non-touching loops, there is only one term, and which is L1 multiplied by L4. So this is delta for you in this example, and then delta 1 and delta 2. So direct path 1 and direct path 2, you can see that pretty much every node is included in the direct path 1 and direct path 2. So every loop is touching direct path 1 and direct path 2. But direct path 3, the loop L1 is not touching the direct path 3. Direct path 3 basically uses the link of G7, and G7 bypasses the nodes of the loop L1. So L1 is not touching the direct path 3. Therefore, delta 3 is basically 1 minus L1, which is basically the same definition as we use for delta, but the difference is that we drop all the loops that are touching direct path 3, and loops L2, L3, L4 are touching direct path 3, whereas loop L1 is not touching. Loop L1 is the only loop that is not touching direct path 3. So that is why we have included that loop in our delta 3 expression. Okay, so now we have identified delta 1, delta 2, delta 3, and we already have direct path 1, direct path 2, direct path 3. So we are ready to apply the Masson's rule for this signal flow graph and find out the transfer function. So what we do is, I have copied some material from the previous slide on this slide so that you don't lose the continuity. So the transfer function becomes direct path 1 times delta 1, which is G1, G2, G3, G4, G5, plus direct path 2 times delta 2, which is G1, G6, G4, G5, and finally direct path 3 times delta 3, which is G1, G2, G7 multiplied by 1 minus L1. And in the denominator there is delta. Delta is 1 minus L1 plus L2 plus L3 plus L4 and plus L1, L4 gain products. So you can substitute the expressions for L1, L2, L3 and L4 in this transfer function, and then you will have your transfer function between Y and R. So this the Masson's rule, it is mathematically proven and derived. Although we have not discussed the derivation and proof of Masson's rule in this lecture, but the Masson's rule is the final authority that you can use for determining the transfer function in complicated block diagrams. So just quickly going through this example once again. So this was Masson's rule. Masson's rule is direct paths into deltas divided by the common delta, and then there are definitions of delta and delta I. Then we have this example. In this example we identified all the direct paths and we identified all the loops. There were 4 loops. 2 of the loops were non-touching. Then we defined the according to Masson's rule, we find out the delta 1, delta 2 and delta 3, and then we just write down the transfer function. So this is how we apply Masson's rule on any signal flow graph. Remember that if you don't have signal flow graph, if you have a block diagram, then first you have to convert block diagram into signal flow graph, which is pretty straightforward, because when you convert signal block diagram into signal flow graph, all you have to do is convert all the signals into nodes and all the blocks into links. So blocks becomes links and signals become the nodes. And wherever there are summing points or branches, you can always use a link of 1, the link of transfer function 1 in the signal flow graph. So this is it, dear students, and I hope that you were able to understand how do we simplify the block diagrams. I had to have you go through all this tedious work of simplifying block diagrams just to make you appreciate and understand the Masson's rule. Now that you know the Masson's rule, you don't have to go through the tedious block diagram manipulations and all the algebra that we went through in this lecture. You can just convert the block diagram into signal flow graph and apply the Masson's rule as we have seen in this example that we did at the end. So that is all about signal block diagram manipulations and Mason's rule. Thank you.